If you're watching this video, it's because you were absent from class, so we're going to do the 3 in-class practice problems, and these 3 problems should be helpful for your homework, so let's get started. The first problem from the PowerPoint is this. The moon is 384 million meters from the Earth. The Earth is 150 billion meters from the sun. What is the net gravitational force on the Earth due to these two bodies? So I'm going to go ahead and draw this here. Here is the Earth. The Earth is gravitationally attracted to the moon. The moon exerts some pull. I'm going to label this force F moon. And then we have the sun. The sun is pulling on the Earth, so the Earth is gravitationally attracted to the sun. I'm going to label this Fs. So the net force acting on the planet Earth, which is in the middle, must be the difference between the force of attraction between the sun and Earth and the force of attraction between the Earth and the moon. So we'll calculate these two forces, Fs, Fm, take the difference, that'll give us the net force. So starting with the force of the sun, that's going to be G times mass of the sun times mass of the Earth divided by the distance between these objects squared. G is 6.67, E negative 11, times the mass of the sun is given, 1.99, E 30, times the mass of the Earth is 5.97, E 24. The masses are in kilograms, which is how that should be, divided by 150 billion meters. 150 billion, that's E9, and we square it. Okay, I'm going to grab the Wabbit calculator here, so hopefully you can see that. Turning this on, 6.67. To get the E, again, it's second comma, negative 11, times 1.99, second comma, 30, multiplied by the mass of planet Earth, 5.97, second comma, 24, divide by, I'm going to open parentheses, 150, second comma, 9, and then square that parentheses. And here we get this number, 3.52, E22 is the answer here, 3.52 E22 newtons. That is the force exerted by the sun and onto the Earth. Now we'll get the force between the moon and the Earth. That'll be big G, mass of the moon times mass of the Earth divided by the distance between them squared. That's going to be 6.67 E negative 11 times the mass of the moon is given 7.35 E 22 kilograms times the mass of the Earth again 5.97 E 24. Divide by the distance between them squared. They're 384 million meters apart. That is 384 E6. A million is 10 to the 6th squared. Again, grab the Wabbit calculator, and if you'd like to use the fraction tool, go alpha, y equals. It pulls up this screen, and choose 1, n over d. So I'll type this in, 6.67 second, comma, negative 11 times the mass of the moon, 7.35 second, comma, 22, times, again, the mass of the Earth, 5.97 second, comma, 24, divide by, down here, 384 second, comma, I opened a parentheses, 6, just to be safe, and then we square that, enter, and we get 1.98 E20. I'm rounding off after 2 decimal places. 1.98 E20 newtons. So the net force on the Earth is the difference between that, when you, the difference between these two numbers. So subtracting the 2 out, and you should get 3.50 E 22 newtons net force. That is for the first in-class practice problem. Next, practice 2, using Newton's law of universal gravitation, show that the gravitational acceleration near Earth's surface is 9.81 meters per second squared. I give you the mass of the Earth. I give you the radius of the Earth. To do this, we need to remember the fact that the weight of any object on the planet Earth is the force of gravity. It's the weight of the object's mass times g, and that the universal gravitation also tells us the force of attraction between two objects. Apologies with that. That's big G times mass 1, I'll call both of these M1, times the mass of the Earth divided by the distance between those objects squared. If the weight of an object is because of the force of gravity, then these two must be equal to each other. So we're going to literally set those two equations equal to each other. M1 times G is equal to big G times M1 times the mass of the Earth divided by R squared. These M1s cancel, and I have little g is equal to big G times mass of the Earth divided by R squared. I'm going to plug in for these values. 6.67 E negative 11 times whatever the mass of the Earth is, that's 5.97 E 24, divided by the radius of the Earth. If something is standing on the surface of the Earth, it is 6.371 E6 meters from the Earth's center of mass, or from the Earth's center. If I grab the Wabbit calculator, we'll plug this in, 6.67 second, comma, negative 11 times the mass of the Earth, 5.97 second, comma, 24, divide by 6.371 second, comma, for the E6, square this, and we get 9.81. That's the strength of the gravitational field near Earth's surface, and it has the value 9.81 meters per second squared. Very familiar with that number. Last practice, the gravitational force exerted by a planet on an object at a distance r is F. What is the force on the object when the distance is reduced to r over 2? So this is just a math sense problem. The first sentence tells us, hey, you have two masses, and when they're at a distance r from each other, you get F. What happens though if we change this r to r over 2? Well, let's see. I'm going to call this our new force. It's still the same value for G. It's still the same value for M1 and M2. M1 can be the object and M2 can be the planet. But now we've halved the distance between them. So notice how I have r over 2 in parentheses and I square that. This becomes G times M1 times M2 divided by r squared is still r squared over 2 squared, which is 4. Here we're dividing by this fraction, this r squared over 4. When you divide by a fraction, it's the same thing as multiplying by the inverse. You can bring this 4 all the way to the top. When you do that, you get this 4 times G times M1 times M2 over r squared. So if I compare this equation with this equation, I can see that they're almost the same. G, M, R squared, all the same. But what changed was this 4. We have literally multiplied this equation by 4, which means that this new force is 4 times the original force, or 4F, or you could say it's quadrupled. So that's how you could answer that question. Expect some multiple choice questions like this where we change the distance. All right, I hope you found this video helpful. Thanks for watching. Study well.